Hey guys, welcome to Module 1, Topic 2, Lesson number 1, where we're going to be talking more about patterns and sequences and all that good stuff. We already did the warm-up. We've already done that, so we're going to go ahead and jump right in to Activity 1.1. So a sequence is a pattern involving an ordered arrangement of numbers, geometric figures, letters, or other objects. A term of a sequence is an individual number, figure, or letter that's within the sequence. So when we say a sequence, we're just saying it's a pattern that's all organized and arranged in some kind of order. When we're talking about the term of a sequence, we're just talking about one of the little pieces within that sequence. So here's the deal. On the next several pages here, which is why this is so many pages, there are 10 examples of sequences throughout this activity. So for each sequence, and you're going to do this for all 10 of these, and there's spaces to help you do that, write it right in your workbook. But for all 10 of these, for each sequence, you're going to describe the pattern, you're going to draw or describe the next terms, and you're going to represent each sequence numerically. So you have 10 of these to go through. It's going to take you a little bit. It's not hard, but it's just going to take time for you to go through all of these because there are a lot of them. So go ahead, hit pause, work your way through all 10 of these, and then hit play when you're ready to check your work with me. Are you ready? I'm ready. I hope you are too. So let's see then. First off, we have positive thinking on number 1. We have a whole bunch of dots arranged in little crosses here all over the place. So let's analyze the number of dots and then describe the pattern. So it looks like I have a dot in the middle and then 1, 2, 3, 4, 5, 6 dots on each side. And then for this one, a dot in the middle, and then 1, 2, 3, 4, 5 dots coming out each side. This one has 4 dots coming out each side. This one has 3 dots coming out each side. So if I were to analyze this pattern and describe the pattern, it seems to me that each side has one less fewer dot, but there's 4 sides, 1, 2, 3, 4. So I'm going to say, if I'm just looking at the number of dots, then I'm going to say that each figure has 4 fewer dots than the figure before it, because each subsequent figure takes a dot off of each end of these guys. So it looks like we're taking 4 dots total off of each figure. So with this in mind, I went ahead and drew the next 2 figure, or pardon me, it doesn't say 2, it says 3. I went ahead and drew the next 3 figures of the pattern. So since this had 3 dots off of each side, I took 1 off of each end, and that meant it only went out 2. And then I took 1 off of each end, so it only went out 1. And then I took 1 off of each end, and I just had the middle dot. There was nothing left by the time I was done with it. Yay! Part C says to represent the number of dots in each of the 7 figures as a numeric sequence. Okay. So I have 6, right? 1, 2, 3, 4, 5, 6. So 6, 6, 6, and 6. That's 24 plus another 1 gives me 25. And then we said we're just taking off 4 dots for each one, right? 1 off of each end there. So fine, that means this first one is 25, the next one is 21, then 17, then 13, then 9, then 5, then 1. You know how this goes. And part D said to represent the number of dots in each of the first 7 figures as a function using a table of values. So I just put them in a table. So here's my first term, second, third, fourth, fifth, sixth, and 7th terms. And we said that there were 25 dots, then down 4, 21, down 4, 17, down 4, 13, down 4, 9, down 4, 5, and the last one only had 1 little dot. I wonder if it's lonely. It's possible. Number 2, family tree. Jessica is investigating her family tree by researching each generation or set of parents. So there's Jessica, and then she looks at her parents, and then she looks at her parents' parents, and their parents, and on and on and up. She learns all she can about the first 4 generations, which includes her 2 parents, her grandparents, and her great-great-grandparents. That's a lot. Yeah, grandparents, great-grandparents, and great-great-grandparents. So think about the number of pattern of parents and describe the pattern. Well, she has, most people have, not everybody. Some of us, divorces and remarriages, we got a few extra, but generally speaking, we have 2 parents. And then those parents each have 2 parents, so we're up to 4. And then those grandparents each had 2 parents, which means we're now up to 8, right? And then all of them had 2 parents, so now we're up to 16. So it looks like it keeps doubling. So each generation has 2 times the number of parents as the generation after it. Fair enough. Determine the number of parents in the 5th and 6th generations. Well, let's see. We had 2, and then 4, and then 8, and then 16. So that means the 5th generation, I'd have to multiply by another 2. So that would be 2 to the 5th power, making for 32 parents. The 6th generation, I'd have to multiply by another 2. So that would be 2 to the 6th power, giving me 64 parents. It's a lot of people. I think that's why they call it a family tree, right? Because it may just start with you, but it branches out really, really quickly. It's a thing. That's why it's a family tree. And then, of course, they wanted us to represent the number of parents in each of these 6 generations as a numeric sequence in the table. So again, I have term 1. So I wrote them down here. So 2, 4, 8, 16, 32, and 64. And then I went ahead and did term 1 was 2, term 2 was 4, term 3 was 8, term 4 was 16, term 5 was 32, and term 6 was 64. Again, those family trees, they branch out really, really quickly as you start going back. That's a thing. Next up, we've got, sorry for the little bit there. Next up, we've got a collection of squares. So I want you to analyze the number of small squares in each figure and describe the pattern. Well, when I did this one, I noticed I had 1, 2, 3, 4, 5, 6, 7, and 1, 2, 3, 4, 5, 6, 7. So 7 by 7, which is 49. And the next one was 6 by 6, which is 36. 5 by 5, which is 25, 4 by 4, which is 16. And so I noticed that the number of small squares are decreasing perfect squares. So it was 7 squared, and then 6 squared, and then 5 squared, and then 4 squared. Working our way down from there. Since this means I need to draw the next 3 figures in the pattern for part B, I did that. So this is 7 squared, 6 squared, 5 squared, 4 squared. The next one needed to be 3 squared. The next one needed to be 2 squared. And the last one was just 1 squared. Again, so lonely. I feel like those last terms are lonely. So represent the number of small squares in each of the first 7 figures as a numeric sequence. Okay, so I did that. 49, 36, 25, 16, 9, 4, and 1. And then represent the sequence using a table of values. Great, so I made the table. Term 1 is 49, term 2 is 36, term 3 is 25, the 4th one had 16, the 5th one had 9, the 6th term had 4, and the 7th term had just 1 lonely square. 1 is the loneliest number that our sequence saw. Next up, press question number 4. We've got Al's house of eggs. Al's house of eggs makes omelets. Al begins each day with 150 eggs to make his famous Western omelet. After making 1 omelet, he has 144 eggs left. After making 2 omelets, he has 138 eggs left. After making 3 omelets, he has 132 eggs left. So think about the number of eggs Al has left after making each omelet and describe the pattern. Well, it looks like we keep going down by 6, right? 150 to 144 to 138 to 132. It looks like Al has 6 fewer eggs after making each omelet. Putting 6 eggs in the omelet. That's a huge omelet. I hope people who order these are sharing with somebody. That's a big omelet. I like omelets. Determine the number of eggs left after Al makes the next 2 omelets. Okay, so Al's making 2 more omelets. So after making 4 omelets, Al has 126 eggs. After making 5 omelets, that means Al has only 120 eggs. So next up, represent the number of eggs left after Al makes each of the first 5 omelets as a numeric sequence. Then represent the sequence as a table of values. So he starts off with 150, minus 6, minus 6, minus 6, minus 6, minus 6. So 144, 138, 132, 126, and 120. And of course, I put that in my lovely table over here. Now, this table actually wasn't quite long enough, so I actually had to do a little bit below. So term 1 was 150, term 2 is 144, term 3 is 138, term 4 was 132, term 5 was 126, and term 6 is 120. Next up, I think we got daisies next, right? Oh, Donna's daisies. So Donna is decorating the top border of her bedroom walls with a daisy pattern. And she's applying decals with each column having a specific number of daisies. And so it's going to look like this. So this is the pattern that she's using to put her daisy decals on the wall. So think about the number of daisies in each column and describe the pattern. Well, it looks like we've got 3 daisies, then 4, then 2, and then 3, and then 4, and then 2. So it looks like she's just repeating the pattern, right? The number of daisies repeat the pattern 3, 4, and 2. 3, 4, 2, 3, 4, 2. She's just doing that over and over again. So with this in mind, determine the number of daisies in each of the next 2 columns. Well, since we're doing 3, 4, 2, 3, 4, 2, that means the next one would be 3, and the next column after that would be 4. So the 7th column would have 3 daisies, the 8th column would have 4 daisies. And you know what's coming up next. We're going to go ahead and represent the number of daisies in each of the first 8 columns as a numeric sequence, and then we'll put it in our table. So 3, 4, 2, 3, 4, 2, 3, 4. Do you feel incomplete that we didn't get to that last 2? Maybe. Again, I'll go ahead and put that in my table. So term 1 is 3, term 2 is 4, term 3 is 2. Term 4 is 3, term 5 is 4, term 6 is 2. Term 7 is 3, term 8 is 4. Yay. We got triangles next, our troop of triangles. So analyze the number of dark triangles and describe the pattern. Well, here I have 1 dark black triangle, and then I have 3 black triangles, and then I have 1, 2, 3, 4, 5, 6 black triangles, and then I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 black triangles. This one's a tricky one. Let me see. I went from 1 to 3, so 1 times 3 seems nice, but 3 times 3 doesn't give me 6, so that doesn't work out so well. Well, 1 plus 2 does give me 3. 2 plus 3, let me see here. This is a rough one, isn't it? So then 3 plus 3 more, and then 6, that'd be plus 4. Oh, so plus 2 plus 3 plus 4. Oh, that's what's happening on this one. So the second figure has 2 more triangles than the first. The third figure has 3 more triangles than the second, and the fourth figure has 4 more triangles than the third. So I added 2, added 3, added 4. Okay, we see it now. We're there. So hopefully you drew the next 2 figures of the pattern. To be honest, I thought it was easier to draw the next 2 figures than it was to figure out what the pattern was. So I drew the next 2. So there we go. They look lovely. So From here, I would have added 5, and then from here, I would have added 6. So let's go ahead and write down, represent the number of dark triangles in each of these first 6 figures. So we have 1, 3, 6, 10, 15, and then 21 triangles. And again, I'll put it in my table. So term 1 had 1 triangle, term 2 had 3, term 3 had 6, term 4 had 10, term 5 had 15, and term 6 had 21. So plus 2, plus 3, plus 4, plus 5, plus 6. That was a tricky one. I'm not going to lie. That one took me a minute. We got there. That one took me a little bit there. Gamer guru. So Micah is trying to beat his high score on his favorite video game. And he unlocks some special mini games where he earns points for each one he completes. Before he begins playing the mini games, Micah has 500 points. After completing one mini game, he has a total of 550 points. After completing 2 mini games, he has 600 points. And after completing 3 mini games, he has 650 points. So think about the total number of points Micah gains from mini games and describe the pattern. Well, if he went from 500 to 550 to 600 to 650, seems like Micah gains 50 points for each mini game he plays. All right, I can handle that. So now determine Micah's total points after he plays the next 2 mini games. Okay, so after 3 mini games, he had 650. So that means after 4 mini games, he'll have 700, and after 5 mini games, he should have 750 points. Once again, I'm going to represent this as a numeric sequence, and then I'm going to put in my table. So 500, 550, 600, 650, 700, 750, and I'll put it in my table. And again, my table, I don't know why they made it too short. My table was too short, so I did a little extra underneath. So term 1 was 500, term 2 was 550, term 3 was 600, term 4 was 650, term 5 was 700, which means that term 6 was 750. All right then. Polygon Party. I've never been to a Polygon Party. Never got invited. Maybe someday. Analyze the number of sides in each polygon and then describe the pattern. Well, we had 3 sides, and then 4 sides, and then 5 sides, and then 6 sides. So each of these figures is a regular polygon. That just means it's equilateral and equiangular. So the sides are all the same length and the angles are all the same measure. Each figure is a regular polygon and has 1 more side than the previous polygon. I got an equilateral triangle, a square, a regular pentagon, and a regular hexagon. You know what's coming up next. Draw the next 2 figures. I don't know about you. I had a hard time drawing the next figure. It was hard. How do you draw a 7-sided figure? I mean, it's doable. It's just not easy. I actually find it easier to draw the 8-sided figure because I do like the opposite sides and it's just easier. The 7-sided guy doesn't work so well. So now we have a septagon and an octagon too. Hooray! You know how this goes. We're going to represent the number of sides of each of the first 6 polygons as a numeric sequence, then represent the sequence using a table of values. So I've got 3, 4, 5, 6, 7, and 8. And of course, I put that all in my table. Term 1 was 3, term 2 was 4, term 3 had 5, term 4 had 6, term 5 was 7, and term 6 was 8. I like the next one. Who doesn't like pizza, right? Pizza, it's good stuff. And I'm cheap, so Costco pizza will do the job. It's not my favorite pizza, but it's passable, it's pretty good, and it's inexpensive. And I'm cheap, so I'll go with that. Jacob is participating in a pizza making contest. Each contestant has to bake the largest and most delicious pizza they can. Jacob's pizza, get this, Jacob's pizza has a 6-foot diameter. This is a huge pizza. After the contest, he plans to cut the pizza So he can pass the slices out to share. I mean, fair enough. It's a 6-foot pizza. I don't think you'd be eating that on your own. So he begins with one whole pizza. Then he cuts it in half. After that, he cuts each of those slices in half. Then he cuts each of those slices in half, and so on. So think about the size of each slice in relation to the whole pizza and describe the pattern. Well, after every cut, each slice is half the size of each slice in the previous cut. We're just cutting them in half. Lots of halves. There's a lot of halves. Determine the size of each slice compared to the whole pizza after the next 2 cuts. Okay, so we had one whole pizza, and then he cut that in half, so that's 1/2. But he cut that in half, so half of a half is a 1/4. And then he cut that in half. So 1/2 times 1/4, half of a 1/4. So 1/2 times 1/4 will give me 1/8. So that means that the next slice would be 1/8 times 1/2, which is 1/16. And that means the next slice cuts would give me slices that are half of 1/16. So 1/2 times 1/16 gives me 1/32. So I just keep cutting it in half, times a half, times a half, times a half, times a half. I think it probably would have been easier if we did C before we did B, but you know, in this case, this is how it goes. So yeah, represent the slice of each pizza slice compared to the whole pizza after each of the first 5 cuts as a numeric sequence. Include the whole pizza before any cuts. And then we'll represent the sequence using our table of values. So I start off with the whole pizza, but it gets cut in half to 1/2. Times a half gives me a 1/4, times a half gives me 1/8, times 1/2 gives me 1/16, times 1/2 gives me 1/32. And of course, I'm going to put that all in my table. Yeah, table. Beautiful. One more. Coins. Miranda's uncle collects rare coins. He recently purchased a rare coin for $5. Got a good deal on it. I don't know what it was. He claims that the value of the coin will triple each year. So even though the coin is currently worth $5, next year it will be worth $15. In 2 years, it'll be worth $45. And in 3 years, it'll be worth $135. Think about how the value of the coin changes each year and describe the pattern. Well, it triples. Each year, the coin value is 3 times greater than its value in the previous year. So times 3, times 3, times 3, times 3, times 3. So determine the value of the coin after 4 years and after 5 years. Well, after 4 years, the coin will be worth 3 times $135, which is $405. And after 5 years, the coin will be worth 3 times that $405, which is $1,215. You know, if her uncle's right, that's a pretty good investment, right? That he bought a $5 coin, and after 5 years, it was worth well over $1,000. That's a good investment. I'll go with that. I'll go with that. So represent the value of each coin after each of the first 5 years as a numeric sequence. Include the current value. Then represent the sequence using a table of values. You know how this goes. So 5, 15, 45, 135, 405, and 1215. And then we'll put it in our table. The first term is 5. The second term is 15. The third term is 45. The fourth term is 135. The fifth term is 405. And the sixth term is 1,215. Yay. Whew, this concludes activity 1.1. Let's go to 1.2. We need all this stuff from 1.1. We're going to start looking at all this stuff that you just did on 1.1, and we're going to use it to help us do 1.2. So there are many different patterns that you can generate, many different patterns that can generate a sequence of numbers. For example, you may have noticed that some of the sequence in the previous activity were generated by performing the same operation using a constant number. In other sequences, you may have noticed a different pattern. So like we had some that was like times 3, times 3, times 3, but we had some that were like plus 2, plus 3, plus 4, plus 5, plus 6. And so Some of the sequences used a constant number every time, and some of them had a somewhat different pattern to them. The next term in a sequence is calculated by determining the pattern of the sequence, and then using that pattern on the last known term of the sequence. So I found the pattern, so I'm going to take where we left off, and I'm going to keep doing that pattern to keep on going to find the next term. So for each sequence in the previous activity, you're going to fill in this table. There's this great big table there on page 93, this big old table. In fact, it's so big, I couldn't fit it all onto my slide, but it fits on your paper. So for each sequence, just fill in the table, all right? So for each sequence, you're going to write, and they gave you the problem name, and you're going to fill in the table. I did fill in the first one for you, but you're going to write the numeric sequence, record whether the sequence increases or decreases. So is it going up or is it going down? And then you're going to describe the sequence by stating the first term and the operations used to create the sequence. So I did do the first one for you. That was our positive thinking, right, where we had the plus signs with the dots. So here is our numeric sequence, 25, 21, 17, 13, 9, 5, and 1. It was going down, so I said, okay, it decreases. And then I needed to describe it. I said, okay, well, I begin at 25 and then subtracted 4 from each term. So go ahead. You're going to fill out this entire table. Again, this whole table couldn't even fit on my paper, on my slide, but it'll fit on your paper. You've got plenty of space there. So go ahead, hit pause, fill in this whole table, and then when you hit play, we'll double check how you did. So I just have it all. Boom, I'm just going to be like, there it is. So we did positive thinking. There's our sequence. It decreased, and our pattern, it began at 25, subtracted 4 from each term. For our family tree, here's the sequence. I really just went to the end of each problem and just put the sequence in here. I noticed it was going up, so I wrote increasing. I hope you use the whole word. Again, I didn't have a lot of space on my slide, so that's why I have D's and I's. I'd rather the whole word, though. So it was increasing. It began at 2, and then we multiplied each term by 2. The collection of squares, here's my sequence, definitely decreasing, I began at 7 squared, and then I decreased the base by 1 while retaining the squares. So from 7 squared to 6 squared to 5 squared to 4 squared on down. For Al's omelets, here's my sequence. It was definitely decreasing, which is fair. He was using the eggs to make omelets. So I begin at 150, subtract 6 from each term. Donna's daisies, 3, 4, 2, 3, 4, 2, 3, 4. Well, that meant that it was both increasing and decreasing, right? Because to go from 3 to 4, you're increasing. But then when you go 4 to 2, you're decreasing. And then 2 to 3, you're increasing, decreasing. So you see the issues. Doing both increasing and decreasing. Begin at 3, continue with 4 and 2, repeat this 3, 4, 2 pattern. Okay. We have a whole bunch more. Our troop of triangles, here's our sequence. Definitely was increasing. We're getting more and more dark triangles. So begin at 1, add 2, then add 3, then add 4, on and on. Our gamer guru, that was also definitely increasing. So begin at 500 and add 50 to each term. Our Polygon Party, yeah, there's our sequence. It was increasing, begin at 3, add 1 to each term. For our pizza contest, it was actually decreasing, right? I went from a whole pizza to only half a pizza, to a fourth of a pizza, to an eighth of a pizza. We began at 1, but then we multiplied each term by 1/2. Or you could have thought of it as dividing by 2. We're cutting it in half, right? So there's our pattern there. Here's our sequence for coin collecting. It was definitely increasing. Good job, Uncle. Begin at 5, and we multiplied each term by 3. So here's what I want you to do. Can you just take a moment, look at your whole big old table. You have a great big table there that you're going to use to help you answer some questions on the next page, on page 94. So which sequences are similar? And go ahead and explain your reasoning. I have some ideas, but I'm curious to see what your ideas are. So go ahead and hit pause and jot down your thoughts on which sequences are similar and why, and then hit play and we'll keep the discussion going. So some sequences increased or decreased by adding or subtracting. Like, did you notice we had like several of them that were like, I'm going to add this or subtract this. So those are the positive thinking, the Al's omelets, the troop of triangles, the gamer guru, the Polygon Party. All of those either added something or subtracted something. So I decided those guys should be similar and go in their own group. But I also noticed that some sequences were increasing or decreasing by multiplying or dividing, right? The family tree, we were multiplying by 2. The pizza contest, we were dividing it by 2, cutting it in half. The coin collecting was being multiplied by 3. So these were multiply, divide kind of guys. And then I just had some weird ones. I had a weird one that just didn't follow any of those patterns. So some followed neither of those patterns. The collection of squares, where it was like square, square, square. So I wasn't actually adding or subtracting. It was just a square thing. And of course, Donna's daisies with the 3, 4, 2, 3, 4, 2, 3, 4, 2, 3, 4, 2. So what do all sequences have in common? I mean, these are all doing different things, but can you give it a thought for a moment and just jot down what you think? What do all sequences have in common? Hit pause and then hit play to continue the discussion. So I don't know about you, and you may notice something different. Maybe you said they all have some kind of mathematical pattern to them, but I noticed that all of these sequences are functions. Yeah. Every input I plug in gets exactly one output. Every element of the domain that I plug in, I get one and only one element in the range. Yeah. So I would like you to consider a sequence in which the first term is 64, and each term after that is calculated by dividing the previous term by 4. So Margaret says, thanks, Margaret. Margaret says that this sequence ends at 1 because there are no whole numbers that come after 1. Jasmine, however, disagrees and says that the sequence continues beyond 1. So my question for you here on question number 4 is this. Who is correct? If Margaret is correct, explain why. If Jasmine is correct, predict the next 2 terms of the sequence. Go ahead and hit pause, jot down your thoughts, and hit play when you're ready to check your work. I hate to break it to y'all. I mean, I'm sure Margaret's a lovely girl and all, but Jasmine was right. Jasmine's the one that's correct. After 1, you can keep going. You can take 1 and divide it by 4. That gives you 1/4. You can take 1/4 and divide it by 4. That gives you 1/16. So it doesn't have to stop at 1. I mean, depending on what it is, you can give fractions. Fractions are numbers too. They need love too. Okay, take care of your fractions. It's important. So what is the domain of a sequence and what is the range? And I'm going to work with you on this a little bit. So the domain of a sequence is usually, when we're dealing with sequences, because if you remember for the domain on our tables, it said term. And we kept writing down 1, 2, 3, 4, 5, 6, 7, 8, blah, blah, blah. That was our domain. So that's the domain. The domain of a sequence is all integers beginning at 1. My first term, my second term, my third term, my fourth term, on and on and on and on. Now, the range of my sequence, though, varies depending on the function. The range of a sequence very much varies. Like we had some that, kept getting bigger and bigger and bigger and bigger and heading toward infinity. And we had some that kept getting cut in half and half and half and half and smaller and smaller and smaller. And it was heading toward 0. But then we had the daisies problem, right? Where it was just 3, 4, and 2. That's it. That's all we get for our range. 3, 4, and 2. That's it. So it kind of depends on the function. The range is going to be very different for each function. But this brings us to one last important little note that you need to know. If a sequence continues on forever and ever and ever, it's called an infinite sequence. If a sequence terminates or ends, it's like that is done and is not going any further. If a sequence terminates, it is called a finite sequence. So sequences that go forever and ever and ever, oh, that's never going to have an end, is an infinite sequence. A sequence that's like, and you're done now, that is a finite sequence. For example, consider an auditorium where the seats are arranged according to a specific pattern. So there are 22 seats in the first row, 26 seats in the second row, 30 seats in the third row, and so on and so forth. And you can see we're just adding 4 seats every time. So numerically, the sequence is 22, 26, 30. And if we were just looking at the numbers, yeah, I mean, it would continue infinitely. However, in the context of the problem, it does not make sense for the number of seats in each row to increase infinitely. Eventually, the auditorium would run out of space. So suppose that this auditorium can hold a total of 10 rows of seats. The correct sequence for this problem situation then is 22, 26, 30, 34, 38, 42, 46, 50, 54, and 58. Therefore, because of the problem situation, the sequence is a finite sequence, right? That auditorium cannot put more and more and more and more and more seats in it forever and ever. There comes a point where it has to stop. There's only so much space. So it's a finite sequence. So with this in mind, the whole idea of infinite and finite, all that good stuff. By the way, when you do, have you seen when it goes forever and you see that ... on the end? Do you know that has a name? It has a name. It's called, and I love this little trivia off to the side. It's called an ellipsis. So an ellipsis is 3 periods, which means and so on. So often when we see an infinite sequence, you'll see that ellipsis, those 3 dots that tell us that it goes and goes and goes and goes forever. So I have one last question for you guys. Does the pattern shown represent an infinite or finite sequence? Explain your reasoning. Hit pause, jot down your thoughts, hit play when you're ready to check your work. So it looks like 1, 2, 3, 4, 5, 6, 7, 8, 9. So I went from 10 to 6 to 3 to 1. Does it keep going or do I have to call it done? I don't know about you guys, but I realized I had to call it done. This is a finite sequence. Each stage results by taking away the bottom row of the pyramid until there's no more pyramid. Oh, I can get there. Until there's no more pyramid. So each stage results by taking away the bottom row of the pyramid until the pyramid no longer exists. And when it doesn't exist, we're done. I can't go forever because there's no more blocks to take away. So this would be a finite sequence. Oh my goodness. Well, as always, guys, I hope you found this helpful and I hope you found this useful. If you got questions or concerns, email me or come see me during office hours. And I'll see you soon. Bye.